Hello learners. Today we'll be starting with a very famous theorem of group theory. It might be famous or older than the group theory itself. This is called Lagrange's theorem of groups. So this theorem is a very fundamental basic block of group theory. So let's read about this theorem. Let's study about it. It says if G is a finite group and H is the subgroup of G, then order of H divides order of G. So this theorem is very important and it tells you about the relationship of the order of the subgroup and order of G. So now first understand what exactly the theorem says, right? What exactly the necessary condition we need to have this theorem. The very important part which we need to have here is G has to be finite. A finite group would actually have this property, because for infinite I would not say anything. I cannot say anything about the order of subgroup or the group itself, because if the group is infinite, how would you actually say this thing, right? So this theorem is basically, obviously it would be valid if G is a finite group. Now, before coming to the proof of this theorem, let's understand some of its applications. So this application says, so if G is a finite group and small g is an element of G, so we are going with the formal notations of the element in the group, then order of G, that small g, that element G, divides order of capital G. I hope this thing is clear. So how would you say it would actually valid, or how we are applying this theorem? I know that order of this G would, this is the subgroup generated by the element G. So this, because as my capital G has finite group, it has a finite order, so this has a finite order, this small g, because it's an element of capital G. So this would give you the elements, this would give a generate an element or generate the group of something like this. So we assume that order of this small g is n. So I know this would give these n distinct elements. After this, it would start repeating. So this would form a subgroup which we already know by the subgroup generated by G. This is the by the definition of this subgroup generated by G. So obviously, if you can count the element, the order of this is actually same as order of G, which is n. Right? Again, it means it's a subgroup of G. It is a subgroup by definition, and we just apply the theorem itself, the Lagrange's theorem, which says because it's a subgroup, it must divide order of G. So this actually is nothing, it is the subgroup generated by G which would divide order of G because it is by Lagrange theorem. Now let's come to the next application. It says that if we have a group of prime order, that group has to be cyclic. So a group of prime order is cyclic. So let's assume that G is our group of prime order. So what I want to say that G must be equals to some P, and it is prime, so it has to be greater than 1. Right? So obviously it means G has order greater than 1. So there must exist an element in G which is not equals to identity. Right? So let G, small g, belongs to G such that small g is not equals to identity. So by the last application, I know that order of this G must divide order of G. But what is order of G? It is P. And you just said that G cannot be E. So order of greater than 1 because it is not identity. So its order must be greater than 1. So the only thing, because the only factors of P is 1 or P itself. So order of G must be equals to P. It means we have got an element in the group itself whose order is actually equals to the order of the group. It means this group is cyclic. We are moving to next application of Lagrange's theorem. It is a very important application and very applicable. It is also called Fermat's little theorem. So what exactly it says, for every integer a and every prime p, a raised to power p mod p is congruent to or equal to, you may use it because we are using modulo, so we can replace it by congruency also. So congruent to a mod p. So this is a very important result in terms of calculation because it actually reducing the the calculation. If you know that a is any integer and p is any prime, either they have any relation or not, doesn't matter. We would always have this thing. You may try for the smaller or simpler one that it would be actually holding, always. So this theorem, obviously we are not actually going into the proof of this, but this is a very, very important theorem in terms of number theory or maybe in many other subjects. You actually use it a lot. This actually going to reduce the calculation a lot time. It is going to reduce it a lot. So the reduction would be so much that it is actually going to be helpful in many of the cases. So if we are applying Fermat's little theorem in general, let's assume I give you a something 14 and you have to calculate it with respect to t is equals to 90. Right? So if I ask you to find, maybe just say, I ask you to find 14 raised to power 40. Right? If I ask you to find this thing, if you have to go through 14 raised to power 40, this number is divided by 90. So I'm asking you find the remainder of this. Right? Or what would you get? Obviously, if you are dividing it by 9, then you would get some remainder. I am asking you to find the remainder. So, because you understand that mod actually going to give you the residual classes. It will give you the residual numbers. Right? So, this would be actually calculating this would be exactly same as, because I know by the Fermat's little theorem that this would give you what? F of 19, a of 19 mod 90 is actually equals to 40 mod 90. We just said. But what you have to calculate? 14 raised to power 40. So 40 means you multiply this thing by 2. This would give you what? 38 and 14 square. So this would give you, this square would be adding here. So this 14 is already there, so square is there, then again one more 14 square is there. So you just square it, reduce by 19, square it, reduce by 19, multiply it, you would get the answer. I hope you are getting this. If 14 square is basically 196, right? So 196 has to be reduced by 90. So if you find it, you would try to get the remainder, it would be coming out to be 6. Similarly, this would also give you the 6. So 6 into 6 is 36. 36 reduced by 19 will give you what? It will be giving you 17. So 17 is the answer. So 17 would be the remainder if you divide this number by 19. So otherwise, you have to calculate all the way. So you can understand the level of calculation. So it actually reduces that thing a lot. Another application It says let G be a finite group and A be an element of G. Then A raised to power order of G would always give you identity. Why this thing would be true? Because I know that A is the element of G. So if G is finite, G must have some order, maybe n. And by the very first application, I know that order of A would divide order of G. It means order of A or order of G must be some multiple of order of A. So if I k this thing as this, so actually this is the thing. Right. Now if you calculate A of order of G, it means A of, right, but order of A, whenever it is raised to power this, it would always give you identity. So this is actually equals to, which is identity raised to power k, which is identity. Hence we have the proof. So we have understood the theorem, we have understood some of its applications, and we have seen that it is very much applicable in group theory and in other fields also. But it's a necessary condition. What I want to say is that obviously if G is a finite group and H is a subgroup of G, then order of H will divide order of G. But the converse is not true. So what I want to say that if G is a finite group and let's say its order is n and k is some factor of n. So this is not necessary that you would able to find a subgroup of G whose order is k. So it might be the case that k divides n, but we would not able to find some subgroup of G which has order k. So the best example for this is A4, the alternate group A4, the group of even permutations, what I want to say. We know that the order of this thing is 12, right? And we know obviously 6 divides 12. But this alternating group, the group of even permutations, doesn't have any subgroup of order 6. Hence, the converse here fails.